advanced Cassandra data modeling. No, it's still too loud. I sound too loud. Maybe it's just me. Anyway, I'm Tim Berglund, and thank you very much for being here. I know it's late in the day. They say it's hard to give talks at conferences. Having been on both sides of the projector, I know it's much harder to sit and learn all day and actually retain things and stay awake. So I will endeavor to make that as easy as possible for you for the next hour, and also try to get you out of here a few minutes early in case you need a little transition time before the next talk. We'll see how that goes. I work at DataStax. I'm the director of training, so my team makes the curriculum that you might find in one of our free online classes, or if you become a customer and you get some of our training, if your company buys training, the instructor who comes to deliver it will be delivering curriculum that my team has at some point made. So, that's me. You are in the advanced track, so I'm going to make some assumptions. Oh wait, I have to give some credit here. It says T.L. Berglund at the bottom, that is clearly me. It also says Patrick McFadden, which is clearly not me, but a substantial amount of material in this talk is ruthlessly stolen from Patrick McFadden, to the point where I thought his Twitter handle should pretty much be on the title slide. I thought it was only fair, so thanks to my colleague Patrick for that. Now you're in an advanced talk, so I'm going to make some assumptions about you. And if these assumptions don't hold, my apologies. But I'm going to assume that you kind of sort of know how Cassandra works as a distributed database. You don't need to know the great and gory details, but sort of how data gets distributed and how replication might work. And a lot of that is going to be separate from our concerns today, but I won't go into big explanations there, so I'll assume that. I will also assume you have at least seen some CQL. Now, between you and me, the really cool thing about this one is even if you have not seen any CQL, you probably have seen some SQL. And if you have seen SQL, then you can fake it in a talk on advanced data modeling with no trouble at all. So that's why SQL is designed the way it is. Now, it's a double-edged sword, right? SQL is, about 4 years old now, and I remember at the time, I was like, oh, that's awesome, because I used to teach people how to use Cassandra, and to describe a query, and literally had to put Java code on a slide to show people how to query the database. Do you know what that feels like? To do that to people. Not that I hate Java, I'm a Java guy, but I mean, really, you have to write code to query the database. That just wasn't right. So, brave new world, we have CQL, and it's this ad hoc text-based query language. It looks just like SQL, so it's easy to learn. It's also easy for you to import all of your relational data modeling habits learned over potentially a long career into the Cassandra world. So the solution architect team at DataStax, and those are sort of like the post-sales consultants who help people make things work. They see the bitter fruits of that practice, people treating Cassandra like it's a relational database. And that's really what this talk is about. It's, for the most part, some use cases, some actual real-life business problems that a person might try to solve with Cassandra. We're going to describe those problems and look at how you can solve them with the Cassandra data model. Now, you can't do that by designing tables and writing queries the way you would do with SQL. So you want to appreciate CQL for the fact that it is easy to learn and accessible, but stop short of acting like it's SQL. So you've got to be careful to forget what you know about the relational model, because you are well and truly not in Kansas anymore. So we're going to look at some use cases, and that's gonna give us an occasion to see the way we would solve certain problems in CQL, in Cassandra, and we will also explore something rather more formal, which we at DataStax affectionately refer to as the Chebotko method, after a guy who works for me named Artem Chebotko. Dr. Chebotko to you. He's one of the curriculum developers who works on my team. He's a computer scientist, and he came up with a fairly rigorous and formal method for turning basically an ERD into CQL tables. It's a series of steps. I'm really not going to teach you that whole thing in all of its rigor and glory, but I'm going to show you what the steps look like. You'll have an idea what it is. It's sort of if you want to do it right, it's kind of like a 4 or 5 hour
sojourn. It's a significant part of a class we teach on data modeling, that Chavaco method. But you're going to get the conference version of it, which maybe not. If we have time, we'll look at maybe a Cassandra 2.1 feature. That's hardly new. Cassandra 2.1 has been out for some months. But there is a particular feature in there that makes certain data modeling problems easier, and so it belongs in this talk. And that'll be, in case you're wondering, user-defined types. We'll look at user-defined types if there is time. All right. Also, I'd like your questions. If you've got them, put your hands up. Tell you I don't know if I don't know, but you are totally welcome to ask things. Otherwise, I'm in transmit-only mode, so ask questions if you got them. All right, so some use cases. Top scores. So imagine you work for some global, profoundly scaled up gaming network. That would be fun work, right? I once did a training event at a company that was a gaming company, kind of in the back end. They made some back end tools, but the way the office was decorated, there was, in the hallways, you didn't have a fluorescent fixture. It was intentionally askance and like blinking. Yeah, they live like that. It's great. So let's pretend to be in that world for a little bit. It was a very, very raucous place. Anyway, so you have a game player out in the world, and that game player, using, let's say, some popular console, is going to be generating events. That events through some API is going to be dumping score data into your Cassandra cluster. All right, that right there is a pretty good fundamental Cassandra use case. I have millions of people all at the same time who are going to do things, and I need to remember the things that they do. These are simply game scores. So that's a pretty sweet thing to do with Cassandra. It looks like time series data. It's really easy to handle. So that API is squirting these scores into the cluster all the time. Maybe this is like a 10-node cluster or something, or 15 nodes. I don't know. That sounds reasonable. All that's going to be, though, is time series. That's just going to be a time-ordered list of, I'm this person, I played this game at this time, and this was my score. We want to know the top gamers of the hour, the top gamers of the day, so that we can put up a leaderboard and gamify our games, create some competition, and make our networks more addictive and all that. So what we're going to do is we're going to take this time series data and we'll run Spark over it. Now, what's Spark and why do we want to run Spark over our data? Well, Cassandra itself, in this case, is going to be super good at kind of an arbitrarily scalable time series array. Again, that listing of scores. Keep them coming. Triple your network, 10 times the number of players. It's okay. We can scale the cluster. We can remember all those scores. That's easy, and Cassandra's great at that. But knowing who had the top score today, that's kind of tough, right? You could imagine doing that in a relational database over a small set of scores. You'd add an index, and you would do a query with a limit in there, and that would be pretty cool. But that is not going to fly when you have tens of millions or billions of rows in a distributed system. So Spark is a distributed computation framework. It is fundamentally an open source product. There is an open source Spark connector that will let it talk to Cassandra. Spark, conveniently integrated with Cassandra, is a feature of the commercial product, DataStax Enterprise. But we're going to run a Spark job, and I literally wave my hands. This is a data modeling talk, not a Spark talk. So suffice it to say that you're going to write some functions that will be vaguely map-reducing. If you know Hadoop and map-reduce things, they will seem conceptually similar to that, but they'll run in a more efficient way around this cluster, and that job will say run nightly, and you'll come back to your cluster, and you'll get your daily top 10 out of your Paxos. Okay, we're there. Okay, we had this problem earlier. There, okay. Keynote's getting a little excited. So yeah, we'll have our top 10 scores for the day. Now, where is that going to go? Well, we run this as a nightly job, and we want now low latency access to that, so Spark is going to dump that into a Cassandra table. All right, do your analysis up into the table, easy enough. Let's take a look at what that data model looks like. Now, this is the input. These are the actual score events. This is what the table would look like for each game that is completed. So this is the time series table here. Let's just walk through this a little bit. Now, second line from the bottom is the primary key definition. You can look at the pieces of that carefully. The first tuple there in parentheses is user ID and game ID. That's what we call the partition key. Now, you know, in a relational database where you have a composite primary key, does anybody else hate that? Am I the only one? Yeah, it seems like most people kind of hate that. You ought not to hate it in Cassandra. It's entirely appropriate. Every time I see that relational data model, I'm like, this is wrong, and we should fix it. But I have to get over that with respect to Cassandra. This is totally normal. The first thing, the user ID and game ID, constitute the partition key. That means that all of the different kinds of games played by that user are going to be local to one machine. That's what partition key means. And the first term of a primary key, in this case it's that thing in parentheses, is the partition key. So you have the guarantee of data locality with respect to a single node inside that partition. All right? Not a particularly advanced data modeling principle there, but I wanted to make sure we were okay. The second field is called the clustering column, and that means that all of the different game instances, so every time I play Tekken 8 as me, every score I get there is going to be a row in this table. And those are going to be ordered by the time that I played them. Now, all of the times I play Mario Kart, don't ask me, this is a weird game network, will also be in that same partition. So all of my games as me will go... back up and reverse that. No, of course that's not true. The partition key, as I just said, includes the game ID. So all of my Tekken games are in one partition, all of my Mario Kart games are in another partition, but they're ordered by time. They're ordered in reverse order. So it's going to be cheap for me to get the newest thing first. That's what that last line does, clustering order by score times 10%. All right. Again, time series data, this is why you have Cassandra. The Spark job writes this. It writes the top 10 stuff. Let's go through the key. See the primary key line, fourth from the bottom. This time, there are 3 terms in the primary key, but the partition key, since there are no embedded parentheses there, the partition key is just game. All right, that means all of the users for that game are going to be in this partition, which stands to reason because this is a top n table. Those will be sorted by timestamp and score. Now, process timestamp is going to reflect the particular invocation of the top 10 Spark job. It's going to run, let's say, at night, and it'll run at a time. And that timestamp that the Spark job runs, it's saying, well, right now, this is your top 10. So we'll be ordering them by score for a given process timestamp, and we should expect to see, for a given game and process timestamp, 10 rows in this table. All right, there's another little bit of funny business at the end, and we really do need to walk through this because this is some slightly next level stuff. We're specifying a compaction strategy. Briefly, compaction. The way Cassandra works inside a node, and I'm hoping you heard this today, and this is a repetition, so I'll just repeat it in cursory fashion. Inside a node, when a write comes into a node, it will sort of buffer those up in memory in a structure called the mem table. Right? And then that's going to fill up, and I always put quotes around fill up because that's a fairly nuanced concept, but it's in memory. Eventually it's going to say, well, I've got enough stuff buffered here in memory, enough new writes, and I'm going to blast those out to disk sequentially, create a new immutable file on disk. And every time that buffer fills up, it will flush into a new file called an SS table. And that's kind of a basic property of a log structured storage engine. Now, once you decide to be that kind of storage engine, where you fill up a buffer and flush it, and there are some nice I/O characteristics that you get in exchange for that architecture.
once you decide to do that, you have made a commitment to occasionally compacting those things that you've written. Otherwise, you'll have this ever-increasing collection of SS tables, and that's kind of a bummer. So the compaction strategy is a thing you're able to choose. That's an algorithm that Cassandra will use internally to compact those SS tables together in the presence of lots and lots of writes. This is a thing that's going to get written regularly, and it's going to get written in a particular way. It's always going to get written at night, and nothing is ever really going to get rewritten in it. All right, so the score data that we had, and we arguably could have applied the same compaction data to that. The score data that we had was time series. This is also classically time series data, immutable stuff that gets periodically written to a table and never deleted or changed in the past. So that is a great candidate for a new compaction strategy called the date-tiered compaction strategy. And we also set an arbitrary time to live there of 259,200 seconds. Somebody check my math, I guess it's a little bit better, 7 hours. So we're saying we don't really care after 7 hours about the old top tens. So we have to run this hourly or more than 7 hours. That combination of a nice close-in time to live and the date-tiered compaction strategy is going to mean compaction on this table is going to be pretty tight. It's going to be efficient and should not burden us. This intelligent management of the fact that we've got time series data. Question?
So, with the time to live, what happens when you get past the time to live? Does it delete it, or is it just going to lazily go away when the space is needed?
Good question. The question was, what happens when you exceed the time to live? Does it, and I'm going to tweak your question, actively go search and destroy, or when it gets around to it? So technically, the answer to that is once a cell at the storage engine level has exceeded its TTL, it will not be readable. So we will be faithful to the TTL. It has to wait. You have to wait until the storage engine has occasion to touch it, but it will decide some later on time to tombstone that cell or that row. So the actual tombstoning, there is no guaranteed latency in which that will happen, but you won't be able to read it in TTL. So kind of at the abstraction, at the top, the TTL works, and then things are going to get sorted out after. Yeah?
Just a quick question on tombstoning. Tombstone is still marked as a used space on the drive, right?
Yeah,
Tombstone
and
item
yes.
is still marked as used space.
Good speaking voice, by the way. I don't even think I need to repeat that, but just in case in the back you didn't hear it. The question was, a tombstone is still used space on the disk? The answer is absolutely yes. In fact, technically, if you've got a data model where you're deleting things, this is not an example of that, but lots of data models, you'll go and delete data. That delete is a write. So you've got the old version that you have previously flushed on an SS table, the last version of that cell. Then you write a new one with tombstone. So it's not just that the data is still there, but you might have written extra stuff. So in the log-structured merge tree storage architecture that Cassandra uses under the covers, one cannot do anything but write and compact. There is no delete. So a tombstone is, in the purest sense, a write. And it's a commitment in the future when you compact the SS table, eventually to expire that thing, so it's not taking up space. But in the short term, it takes up space.
Right, so you have to compact it in order
We'll have to
reclaim the space.
To reclaim that space, yes. And this data model, this is sort of a best case for compaction. You're kind of getting away with murder. It's pretty good. Other question? All right. Here's how we read. Okay, back to that table. Get this, nope, wrong. That table, get that in your head. You've got the game UUID, the process timestamp, and the score. Those constitute the primary key. So how are we probably going to want to query this? You're going to say, well, I want all of the Mario Kart scores between 2 and 3 p.m. Or the top 10 job that ran between 2 and 3 p.m. for Mario Kart.
That's really what you want. So let's go ahead and look at that query. So let's select those columns from top 10 where game ID equals that UUID. It's common to see UUIDs and not integers as surrogate keys in Cassandra. I'll come back to that. Where the process timestamp is before 2 o'clock, limit, typo, I should say 10. That's shameful. That says 1. That's obviously it should be 10. Thanks for calling me out on that. Okay, yes, you want the 10 most recent. You don't even really need a bracket on the time. You can just say, you know, the last one that happened in the past hour. That'll be my current top 10. Why is that a UUID and not an integer? See, as a teacher who needs to make slides that look nice, rage, right? Nobody wants to look at a UUID. It's terrible. This is a kind of a short query, so I can make the font real big and get away with it. But there's times, believe me, when you're trying to lay out a slide, it's a hassle. So that doesn't make me happy, but why? Just think to yourself and answer, would we do this to ourselves? Typically, if this were a single server, single master relational database, that game ID would probably be a nice, polite, monotonically increasing integer. If it were Oracle, it would be a sequence. If it were MySQL, the auto increment. Would we not love life? It's great because they're relatively easy numbers to look at and think about and put on the screen and all that. Well, that's not possible in a distributed system at scale. All right, there is no one place to go to increment that counter. If you're thinking, wait a second, Cassandra has counters. It's a different thing. There is no one place to go in the representation of this table to get the next ID. Because if this is a 10-node cluster or 15-node cluster, there are 15 nodes on which this table exists. So I'd have to go lock and ask them all and calculate, and then I could write like a few times a second. You get fired. So UUIDs, of course, I can randomly create. That is not accidental. It's very common. And it more or less has to be that way because it's distributed. So that query will produce this nice list of scores, and we'll see, it looks like Trinity had the high score in the 1 o'clock hour, followed by Neo, and so forth.
Surveys of guaranteed facilities calculating it.
Right. Is there a way to guarantee the uniqueness of the UUID? No. And it's I don't know the actual numbers, but I think UUID collision is sort of like, am I going to die by meteorite today? It's on the order. It is a respectable question, so I'm not making fun of the question. It's reasonable, but there are enough bits in there that as long as the random number generators are even a little bit random. Right. And the UUID generator that you would use in the insert for CQL, they're good. It's the way you generate surrogate keys in Cassandra, so collisions are in the category of I should literally worry about dying in weird ways before I worry about that. Nobody does. So. But fair question, because one could do that wrong. CQL doesn't. So
the other side of that, though, when you're trying to generate a unique ID for a game like Mario Kart, what's the guarantee you're not going to get two different IDs?
When your question is when you're trying to generate a unique ID for a new game, what's the guarantee you're not going to generate two unique IDs? So this is at the point when I would have like two clients administratively, two admins creating that thing. Good question. Good question. Slides later.
Okay.
Yes. That kind of falls into a use case I call user account creation. That's the canonical use case for that. But same thing. Same exact thing. Yeah, it's a problem, and we fix it. And back there to the team. So. What's the performance? Yes, okay. The question is, what's the performance impact of compaction it is non-zero, and there isn't a, I mean, it depends on too many factors of the system, but I'll say as an operator of a Cassandra cluster, you need to take measurements carefully. So if you're measuring latency on a particular node and no compaction is happening there, and you're like, oh, I'm cool, and you don't measure during compaction, that's a problem. So you need to take an average over during compaction and not during compaction. If you're making measurements, you should create write traffic to trigger compactions during a long experiment. Compaction is a part of the work of being Cassandra. It isn't. You shouldn't think of it like life is we're going along and life is good, and oh crap, now I have to do a compaction. It's an ambient condition. It happens sometimes, all the time. You just need to make sure your measurements account for compactions. So put that a different way. If you did a benchmark where there was no write traffic and only a bunch of reading going on, and you thought you were okay, you would not be okay. You would not be getting statistics that accounted for compaction. So it's a thing. The impact is real, but that just goes into your latency measurements and your cluster sizing. And question here.
How Cassandra handles the metadata of the unique IDs of the game?
How does it store the metadata? Well, the unique ID would be data. If I'm understanding your question correctly, the metadata would be the table schema. And there's an internal table and an internal key space where that gets done. I mean, Cassandra has an internal mechanism for keeping track of metadata. But the ID itself, that's just saying, I'm a table called top 10, I have a column called game ID, and it's type UID, and that's handled inside the system key space. So get a cluster up, use the system key space, use system, and poke around at the tables, describe tables, and look what's going on. Yes?
It's long. Is that
UID, it's long, takes up a lot of bits. No, I mean, it doesn't take up that many. You'd have 8 bytes for an integer. Yeah, I think you're gonna sync up the table in other ways first. But partition size is a concern. We'll come to that later. Back up.
I'm a little bit confused about the ordering of your clustering columns. If you're looking to pull back limit 1, limit 10, and the top score,
Yeah.
I thought you have the process time before the score. So,
Yes.
would you be pulling back the latest time or the highest score?
I want the highest scores at a given time. So my process runs periodically. I'm going to say it's every hour, and it'll dump its timestamp in at the time that it runs. So I'll want sort by game, sort by process timestamp, and then each time the process runs, it's going to squirt 10 rows in here of the top 10 scores. So I'll sort by game, then time, then score. So it's legit. All right, yes?
All-time high scores.
All-time high scores, you would write another job that takes the output every day and then has an all-time table and sorts with those and cuts off to the top 10. That's just a factor of Spark. All right. I did ask you to ask questions, and it seems you were delivering. All right. Keep going, guys.
Are you supposed to be done? Or
Yes.
Okay, so.
Well, done with that use case.
Oh, okay. I'll wait until.
Okay.
I just have general.
Okay, cool. And if we don't get it, if you don't get back to it in this session, find me afterwards. All right. That applies to everybody. Spark, okay, we kind of covered that. It's a distributed computer framework, super cool, integrated with DataStax Enterprise, open source project all its own, project with a life of its own, great team behind it, worth checking out. Let's go for another use case. File storage. You decide that you got a great new idea for a startup, and you're going to go after the big money in image storage. Yeah. You want GIF hosting. It's a personal favorite of mine. That's great. Somebody sends you an email saying, "Hey, sorry about whatever.
That's all. That's all the reply needs to be. And they understand. So, you're going to use Cassandra as your storage backend because you don't just want to store the bulk data, but you also want to store access times. You'll be able to kind of gamify things, say these are the most popular images, don't you want the most popular GIF, blah, blah, blah. It's your social image storage startup. Personally, I think you're a genius for that. But those are going to get stored in Cassandra. Now, let's talk about some things that we want to do. All right, these are not really described or written in the form of user stories, but these are the 4 things we want to do. People need to be able to create accounts, they need to be able to upload images, people need to be able to get to those images from anywhere. They can read a particular image out, and people can check how their images have been accessed. How popular is my funny cat GIF? I want to know. I'll confess, I'm a pretty big GIF user. I'm not a big GIF producer. I've made a couple, and I think they've been pretty good. I have pretty high production quality standards, but mostly a recycler like everybody else. All right, now, these are the things that we want to do. Now, in Cassandra, we'll see this later if we get to the Chewbacca method. We'll see this later, that you don't just consider objects out in the world. That's what you do with a relational data model, right? What are the things out there? How do they relate to one another? What are the cardinalities? What are the relationships? You think about entities, nouns. What do I do with those nouns? What questions do I ask about them? You don't really go there because you just let the queries emerge as you build your application. You write something in SQL, and it works good enough. If you're lucky, as long as the system's not too big. That's kind of what we got away with. In Cassandra, not so. We do, as a matter of first importance, look at access patterns or the queries that our application will run. So, following those stories, we will be able to read a single image, get all images in a particular time range, get specific images over a given time range, and read the times an image was accessed. That's going to be time series data. We just want that big chunk. When was this image accessed? Maybe we can do some analytics on that. Those are the things that we're going to do, and let's look at the tables for doing that. User creation, and I'm gonna go ahead and make this easy for now, but this will be our user table. We'll have a username, a first name, a last name, and a list of emails. Now that's not a new feature. Collections have been around, so what, 1.2? That's a list of strings, that last column. Emails, list of strings. Now, that looks bad to relational eyes. And why is that?
Emails.
What's that?
It's not normal.
It's not normal. It's not normalized. It's not, I mean, I get this nice little syntax sugar here where I have a list. So I don't have to say email 1, email 2, email 3, email 4, that kind of thing that we've all seen. Certainly none of us in this room have done, but you've seen other people do it. And this is better, certainly better than that, because it's a variable length list. Where I have some latitude. Technically, in terms of implementation limits, like I have 2 to the 16th minus 1 emails. Something's probably fishy. If you have that many emails, you're probably up to something. But it's a list. That gets me out of a foreign key. Now, Cassandra, I think some people sometimes say Cassandra doesn't have foreign keys. I say, anything has a foreign key. Okay, I have a notebook with a foreign key. Like I said, hey, go see this other thing that I have uniquely identified. Go ask this person a question. You know, it's a pointer, right? Of course Cassandra has foreign keys. What it doesn't have is foreign key constraints, and it also doesn't have joins. And so if I wanted another table of emails that had a foreign key back to the user table, that's a bad thing. It's not an impossible thing. It's not completely against the Cassandra rules, but you super duper don't want to do it. You want to try to find a way around that. And so lists here are a way of nesting that email data and, frankly, denormalizing that email data in a pleasant way inside the user table. And if you have any compunction about denormalizing, my advice to you as a Cassandra data modeler is to build a bridge and get over it. Yeah,
have to start thinking of this as an okay thing. Let me give you some tools for that, because I know it can be difficult to make a condition, right? The thing is, at scale, you're going to do it anyway. All right, if you make a beautiful, normalized relational data model, it works when it's small. And then when it's big, and you can't buy any more hardware, and you can't pull out any more fancy optimizations that you hired an expensive DBA to do, and your reads are slow because the database is doing all this joining, you're going to denormalize. I mean, that's just what one does. It's one of the compromises that you make when you scale a relational database. Cassandra is being upfront. Relational databases, hypocritical. Cassandra, honest.
How deeply you can nest the normalizations?
What's that? No, you can't nest collections at this time. Question back there? Correct. Okay, so I will be fair to call it an honest objection. It's not like denormalization is all roses. Okay, there are bad things about it, like duplicated data, things you get out of date with respect to each other. There are no silver bullets for that. So a good data model is going to be aggressive about denormalizing, but not too aggressive. You're going to balance that. And I want to say, typically, the client-server model in which relational databases evolved was, here is my schema, let it evolve over time, and there are 10 applications doing things to it. And we let those applications evolve independently of the schema, and so it's appropriate to have constraints and security features and, normalization to keep that data sane. The world in which Cassandra has grown up, and the typical Cassandra application, is that there is one program, one application that talks to this database. And so that kind of stuff is easier to get right. It's not perfect. You will duplicate data. Things will get out of sync. You have to create mechanisms to deal with that. None of them is magical. But the problem is less severe than it seems. And again, this is one of those things where if you're going to be scale, if you're going to work at scale, you have to do it anyway. So either you have to do it in an ad hoc and backwards and piecemeal way with the relational database, or just in a straightforward way, planning for it in Cassandra. So it's a problem. And it goes in the category of distributed systems that are hard. Which I don't say flippant. They're also awesome.
So what's the sweet spot? Because even in this example, I have seen normalization in table. So you have a user table and you have a video table, right? Let's say, or your user table or your game table. You do have something like user game, which stores the new IDs of user and the game, not necessarily the content of the user of the game.
Yeah.
So we kind of do the normalization over there.
Yes, you saw that in the last example where there were things that are, by my definition, foreign keys. So it's not illegitimate to do. But here, the impulse with a relational hat on would be, get those emails out of there. And that would be 100% wrong in Cassandra. You want to nest that here. So there are truly independent domain objects which simply have to refer to one another. And that's okay. If it's so the first three things you do are denormalize, denormalize, and denormalize. After that, if you're upset about referential integrity, you can write a Spark job that nightly will sweep through things and look for integrity violations. That's the sort of thing people do. And that's the sort of thing people do in relational databases when they disable constraints. So the same thing. All right. Creating a user would look like this, and there is an important little piece of green text, 3 words at the bottom of that query. Insert into user, these 4 things, DL Berglund, Tim Berglund, blah, blah, blah. There's my list of email addresses, work and personal. If not exists. It just like snuck in there, was hoping you wouldn't notice it. It's not going to get away with that. We're going to come back to that text in a minute. It's profound, and like just about nobody in the world understands what's going on under the covers with those 3 words. So I'm going to try to make you some of the elite core of people who kind of get that. All right, let's go through keep going through the data model. An image has a unique ID. You see I skipped some data types just for convenience here. There's a user that the image belongs to. There's a creation time. There's an image name. There's a list of tags. And there's a map down at the bottom of images. Now that list of tags, that's just tagged images, of course. On our social image sharing site, we're going to have tags. That problem stinks in relational databases. It's terrible. And this was a thing 10, 11 years ago when tagging was new and Web 2.0 was exciting, and people said, unironically, there were things like Delicious and Flickr that made up the ideas of tags. And they were solving these problems in relational databases. It wasn't pretty. You guys had neat blog posts back then about how those things were solved. Here, if I were using the enterprise version, I would use the Solr integration to search those things. That would be relatively straightforward. I would just search them as full text, and I get pretty performant tag searches. I also want, the reason images are a map is I want like a thumbnail and an original and a medium. Maybe I want different sizes of the image. So I'm gonna kind of make that, like I would have had probably a join table for that, but here I just have this map that says here are 3 UUIDs, what are those? Foreign keys. Here are 3 foreign keys to some other table. That other table being, not that, this. No, this. It's alright, we skipped a couple tables, but just managing time. The image table points to this guy, and a blob is just a blob. It's an image. It's really what it's going to be. It's not an image in the abstract sense, but it's a file. And we're going to chunk these guys. We're going to chunk them because an image might be really, really big, and this starts to get into a practical consideration. That's something you need to think about when you're storing data in Cassandra, and that's how big can a table column get? How big can a row get? How big can a partition get? These are implementation limits. If we're solving a problem like this problem puts that front and center. All right, how big can a column get? Maybe a few megabytes is good. Maybe 10, just as a general rule of thumb. There are no hard. Well, there's a hard limit. It's 2 gigabytes. Do not attempt. A small number of megabytes would be nice for a column size. Now we'll look at our chunk table in a minute, but we have to chunk because we can't just put that whole image in one place necessarily without an artificially low size limitation on the limit. So this table lets us store a number of chunks. We've got chunk count right there, and blob chunk, here we are. This guy contains the actual data, and that first column there, object ID, is going to be a foreign key back to this guy. All right, so every blob is going to point, every blob chunk is going to point back to the blob of which it's a part. This is not hard to understand because we do this. This is a somewhat normalized data model.
Just a question though, I take it that the chunk ID though, if there's some sequential, should be sequential, otherwise you're not going to know the order to reconstruct the image.
Correct. The question is, chunk ID has to be sequential, and Mr. Speaker, you said that you can't do sequential things, so what do I have to do there? What's my game? It is a correct observation.
In the application?
In the application. Meaning, when I'm chunking a new image, single thread. So chunking of the image can't be distributed. It has to be me in this thread or these locked threads on this core doing the work, incrementing account. And that's in the scope of this case, this use case, that's legit. One could imagine data that's so big that you have to distribute the chunking and you'd have to do something different. And I wouldn't like the thing you have to do. Maybe get a different job.
There's
Okay, what am I, help me out here, guys. My partition key is object ID plus chunk ID, so those top two things. Meaning, I expect all of my chunks to fit in one partition. So I'm node local with all of my chunks. That means a whole one of these blobs will be on one computer. That means I need to be aware of how big a partition can be. What am I comfortable with in terms of maximum partition size? And a good rule of thumb is 100 megabytes. You may be able to violate that and meet your performance SLAs. It's not like the world is going to explode, but when people ask how big a partition can be, the stock answer is, 100 meg. Yes?
Maybe I misunderstand, but did you say that so the combination of different chunk ID hashes into something that occurs in partition?
Yes.
So I chunks, each chunk I need a different value, translates the combination of different chunk ID.
Yeah, this is the second time I've done this. This is me being bad at counting parentheses. I make a tap into some of. Actually, not a horrible closure programmer, but there are tools to do that. So, yeah, you're right. I'm going to be able to put those in different partitions, meaning I've got arbitrary sized files. So, back there. Yes. Yes, and we might get there. There are slides for that. It doesn't look good. But it's way more fun when you guys ask questions, because then I know I'm at least telling you things that you want to know. Yes?
I'm just wondering, if you had this as partition key being the object ID and the chunk ID is just a clustering ID, could you order them that way?
You could order them that way, but then that would give you, so I misspoke before, that would give you the one partition limitation. If you were cool with that one partition limitation, then you get, well, you still need to generate, the chunk IDs, but you could use a time UUID, or there's other games we play.
So you're saying if you did that, you would limit that image to that one partition?
One partition. And maybe that's okay. I mean, 100 megabytes for a GIF. Yes?
But if data doesn't match this partition, with this key, so you're saying that it should be the same partition, but what if it doesn't fit the partition?
If the data doesn't, so if you have one chunk that's too big for a partition, you can determine that in the application. So you're the one who chunks. So make sure the chunks get bigger than 100 megabytes.
I defined this partition key, object ID, chunk ID, but at some point the data doesn't fit anymore. One machine. What will happen?
But every new chunk you create goes into a new partition, so it'll be distributed around the cluster. Now, if the question is, what happens when I run out of storage, which you're going to do, right, at computers? I don't think that was your question, but...
No, I mean, well, when you have an object ID and chunk ID, and expect that the same object ID and same chunk ID will be sitting in one storage, one machine.
Right.
So what if it doesn't fit that?
Got it. Well, it's up to me to chunk, right? The application that's loading images does the chunking. So I'll say, I will never make a chunk bigger than 10 megabytes. I can make that guarantee. So the chunking is there for me to do. I can make sure that the chunks fit. That do not look satisfied.
So you got only 2 megabytes left on that machine, specific machine.
Oh, yes. Okay. Okay. You didn't operate the cluster well, so it will fail if you run out of disk space. That's really the question. You're trying to write a partition to a node that doesn't have disk space anymore. You will die. So you should have. And I don't know if I'm answering the right question. Maybe we should talk out. But
we have space on other machines.
Right.
It's still
got it.
There, right?
Yeah, space on other machines. This one node is out of disk space. You don't have any control because those things get hashed. In any sensibly deployed cluster, you don't have any control over what node that partition gets stored on. So if there is one node that's out of disk space, you're toast. All right, let us move to this intermittent. 11 minutes left, and I want to talk about Paxos. I'll get upset. I'll get upset. That's too strong. I'll be disappointed. All right, let's talk about this problem. Now, for users, you asked before, what if two people are creating a Mario Kart row at the same time? A better question, what if two people are registering for my social GIF sharing startup internet website at the same time? That's a real problem. So let's imagine we've got two coordinators, so two different nodes, having writes come in from the application here. And the way I got to do this is I got to see, well, does TL Berglund exist as a username? And this other this other thing is going to another node is going to check that. And I actually got a typo here. There, take that away. That'll work better. Two different users are trying to sign up at the same time. All right, I'm TL Berglund. There's a guy who lives in Stockholm. His name on Twitter is T Berglund. Sometimes he gets tweets from me. I think I owe him a beer, some regularity. So there's this poor T Berglund guy. Actually, he and I were signing up on Twitter at the same time. We both wanted TL Berglund. Well, who gets it? Right? He comes in here, this coordinator. This guy comes in here, this coordinator. He says, "Well, is TL Berglund there?" And I ask, "Well, is TL Berglund there?" Both applications are told no, and then boom, boom, they both issue writes at the same time. Who wins? So that's a real problem.
Who wins when?
What's that?
Who wins when? In replication?
Exactly. They're well, that's going to depend on consistency level. Let's just say it's a race. Yeah. The problem is still who wins. So here, what we need is a transaction. A transaction would be nice. Now, we don't have ACID transactions in Cassandra, and I don't know that they ever will exist in any way that performs well. That's not generally the thing that you could do in a distributed fashion and make it run fast. But we do have a feature called lightweight transactions. It uses this really cool algorithm called Paxos, which basically nobody really understands. But you know what? It does work, and it is super easy to use. That's the nice thing. The syntax for this is crazy easy, and you can read the Paxos paper, you can read the Paxos Wikipedia article, and you can struggle through that, or you can just like, hey, let me use the CQL. It's great. So what you do is you just say, hey, I want to insert into users a row that has the username TL Berglund if it doesn't already exist. And the other coordinator, same thing. He's going to say, hey, I want TL Berglund if it doesn't already exist. And the way this works is, let me just give you a quick idea. Changing domains to coffee for a minute, borrowing from something else here. The coordinator is going to say, well, okay, we want this new thing called flat whites. We go to this prepare phase and sends a message to all the replicas. He now becomes the proposer. He generates a unique sequence number for that partition, and he says, hey guys, I'm going to propose with that unique sequence number, of this in this case 1, that you all take this new value. All right? And they're going to say, well, nobody has given me, on this partition, a better sequence number than 1. Nobody's promised me anything higher than that number. So you know what? I'm going to go ahead and accept that. I'll say, yeah. If nobody gives me anything better, I'm definitely not going to take anything lower than 1. This is step 2 here, the promise phase. All they've promised is that if nobody gives me anything better, I'll take your sequence number. I certainly won't take anything less than that. And so the proposer says, okay, I can make progress. A quorum has told me that they would take that proposal. So same thing. Okay, guys, good news. Here's the same right. Take it. They all take that. And in the meantime, the happy path here, nobody has given us any higher sequence number in that replica set. So they will accept it. They compare the sequence numbers. They accept that and send that number back. Now, what would have happened if, in the meantime, somebody else had jumped in with some other value to one of those nodes in that partition? Well, if it had a higher sequence number from the time they had accepted the original proposal, if someone came in with a higher sequence number, they'll take a better offer. And so when the acceptance message comes back from the proposer, they're going to say, no, actually, I don't want that. I'm going to take this higher number. And the proposer will then say, okay, I thought I was getting a flat white, but you want an Americano now. But that's okay. So now, guess what, guys? I'm writing Americano now. And the proposer sort of upgrades itself on the basis of the best offer that the acceptors have gotten. Now, look, it would take an hour to go through the reasonable cases. This is the quick and dirty sort of insult to Paxos. I do recommend you read the paper and you read the Wikipedia article. No, you're not going to clap. It's complex, and all the various failure modes are nasty. The upshot is, if not exists, means you can create user accounts and you won't step on each other. You can also put expressions in terms of values inside the partition that if not exists.
Is it only going to compare on the keys or complete records?
If not exists is going to compare on the primary key, so if that row doesn't exist. Otherwise, you can put expressions in there and there, whatever you say. So, all right, with 4 minutes remaining.
Question.
Yeah, let's just do questions. Go ahead.
So obviously you need at least 4 consistency level. Where, at what level do you define that? I mean, is there any way that you could make that not work?
There is a consistency level called serial that you'll use if you want to use language transactions. Implicit, in the table definition or something. It's not simple.
Regardless of how I connect or create the table or do anything, it can never go wrong. Or is there something I need to make sure?
You want to use the serial consistency level and if not exists language string in the query, and that makes it turn.
Is it still for updates? Same language transaction, same not exists, or how does it work with update?
Is it same? With update, yes. Update is same. And of course, performance penalty, right? You don't get it for free. There's this chatter. You're not going to get a 2 millisecond write, but you're not going to do everything inside a transaction. There's a few things that need to be done that way. All right, last question.
Does he acknowledge the act going back to the client who then ends up the whole thing that is all down? How many people that asked for?
Yes. Yes. High latency write relative to the home is going with that. All right, my friends, thank you. You guys are awesome. I'll hang out with you.